Okay, hello everyone. Good to see you again. Good afternoon. Hello online people as well. I hope you can hear me. I hope you can see me. And hello to Sebastian if you are watching us. Sebastian is right now in Argentina, so today is gonna be with me. Yeah, Sebastian is attending Eco Party in Argentina and meeting other students of this class, and I guess he's having fun. Okay, so today's class is going to be about binary exploitation. We are going to be writing a lot of exploits. It's going to be very hands-on, very practical, a bit of theory, but it's going to be fun, I promise. But before we get to that, some organizational notes. Okay, so data from the last week feedback. How was the class tempo? So majority of you think it was all right. It was the class on lateral movement. 15% thinks it was too fast. Surprisingly, no one thinks it was too slow. Okay, so overall, pretty good. Just please keep submitting the feedbacks. We are reading it, and even the text that you've written in the notes. So we are trying to make it better, the class, based on the feedback. And some other notices. So for you, like CTU students who are attending physically, next week class is not going to be in this room. It's going to be happening in the 301. So that's the class above the buffet, like the other aula, which is a bit smaller. So please, next week, go there. We will mention this again in metrics in the announcements channel. So please read that if there are some other news about that. And nothing is changing for online students. The recording and the live stream is going to be as usual. And there are no Pioneer prizes because last week there was no assignment, so you can keep resting. All right, so regarding today's class, we are going to be speaking about binary exploitation, specifically stack buffer overflow and also return-oriented programming. We are going to be writing a lot of exploits. So it's going to be hopefully fun. And at the end of the class, there's going to be a small part where we also touch fuzzing techniques, basically a testing technique. So a bit of the motivation for you guys. When Mures had his deception class, he started with a magic trick. So I'm going to start also with one magic trick. So look at this C source code. So I'm going to assume in this class a little bit of knowledge of a C programming language and also Python. But if you have any questions, please ask me. I'm happy to try to do my best answering everything. So look at this small C source code, what it does, right? So it just creates a local buffer that has a static size of 64 bytes. Then we read the user input, and then we just print the user input back to the standard output, right? Pretty easy. Like, what could go wrong, right? Okay, so let me just show you pretty fast. In here, I have the same C source code that you just saw. See, nothing weird. I have also one makefile that compiles the source code. It's just GCC compiler without any special flags, nothing whatsoever. So let's just use it. Okay, there's some warning, like, who cares, right? It was compiled, so it has to work. Okay, so there is our main binary. I can try to run it. It expects the user input, so I can do hello world. And it's working, right? So it just prints it back to me like everything we expected. Okay, but I have also this Python script that all it does, that it outputs this weird noise, garbage, bytes, whatever. So it just prints something on the standard output, right? So let me show you a magic trick. What happens if I do this weird command, which basically just outputs the bytes to the binary that we produced. Seems innocent, right? Okay, but I have a shell. See, I can do anything I want. I have a fully functioning, powerful shell. I can echo something. I can read files. See, there's our makefile. There's our, okay, not this one. There's our C code. Okay, so this is the code we are running, and suddenly we have shell, right? So pretty impressive, no? Like, how is this possible? So this is a bit of the motivation on the beginning of the class. I'm not going to explain right now what is happening, but at the end of this class, you should be able to understand what's happening and write the magic Python script exploit on your own. So hopefully you will understand everything and you will be able to write the script on your own. And we can move to a bit of explanation. So binary exploitation. Does any one of you have any experience with that? So for example, in a capture the flag competitions at work or during your free time? Nobody is exploiting binaries in your free time? Come on, what are you doing in your free time if you are not exploiting binaries? Okay, so I have a small definition here. So basically what it says is binary exploitation is the act of subverting a compiled application so that it fails in some manner that is advantageous to the exploiter. So we are going to be working with some compiled applications, and we are trying to find some behavior that is hidden in the binary that we can basically take to our advantage, right? So if you think about programs like in a theoretical sense, like all programs are like state machines, right? They are in some state and there are like tons or maybe infinite number of states, and you have edges from the states, like you can move to take some edge to some other state. So in the binary exploitation techniques, what you are trying to do is that you are trying to find the edges that were not intended to be there. Like the binary should not allow you to do this exploitation technique that is advantageous to you, but you are exploiting like a bug that, for example, the programmer introduced, or there is a bug in the operating system or in the compiler or anywhere in the full stack. Like before you run the binary, there's a lot of magic happening. So you are trying to exploit some behavior that is advantageous to you, but it's not supposed to be there, right? So this is the theory. In practice, it's quite difficult because it depends on a lot of different scenarios, like what access do you have to the binary, right? So, okay, you can have access to the source code, but maybe you don't. Maybe you have access only to the binary, but maybe you don't have even that. Maybe there's just like a network socket, and there's a binary running on some server, and you can only like put a standard input and see standard output, right? So you don't even know the source code. You don't know, for example, the operating system where it's running. You don't know the architecture of the computer. So it depends a lot what you know and what you don't know. Because if you have, for example, the C source code that we saw, and if you compile it on Linux, and then you just copy-paste the binary to, for example, Windows, it's not going to work, right? Because you produced like executable for Linux, it's not for Windows. And so if you are exploiting binary on Linux, it's probably not gonna work like exploiting the same binary or like the same source code on Windows. It also depends on architecture of the computer, right? So if you have, for example, x86 computer, you produce different binary on the same operating system than if having like ARM processors, for example, that Apple is putting nowadays into the latest MacBooks. So it depends a lot on the context, like what you are trying to exploit and how and where and stuff like that. So examples of binary exploitation. So for example, one of the most famous one and the ones that we are going to be focusing in this class is stack buffer overflow. But then you have also heap buffer overflow that is basically the same, just overflowing different parts of virtual memory. Or you have format string bugs. That is when you use user input and you put it directly to the printf function. Attacker can basically print any part of virtual memory and steal, for example, secret keys and do anything he wants. And binary exploitation is quite similar to reverse engineering. So you will have a class on reverse engineering next week. It's going to be covered by Muris. And the difference that I see in binary exploitation and reverse engineering is that in binary exploitation, you are trying to exploit the binary like only for your advantage. Like you don't really care what the binary does, right? You are trying to understand it only as long as you can really exploit it. In reverse engineering, whatever you are reversing, like you probably want to know what is happening under the hood. Maybe it's a malware, right? So you want to know everything what the malware does. You are not trying to exploit the malware. But of course, sometimes when you are exploiting a binary, it also comes with a bit of reverse engineering because you also need to understand what's happening there. Okay, so now a bit of the theory. Nice, I have rewards for you guys. Okay, so a bit of the theory. I'm still talking about binary, right? So what is a binary? So what we are going to be talking about are executables, binaries. We are going to be focusing primarily on Linux ELF executables, and we are going to be talking about x86 Intel 64-bit architecture. The concepts are very similar. For example, if you are having the latest MacBook with ARM processors, like it's going to be similar, but the processor is different, so the binaries are also different. And yeah, still, like vast majority of computers nowadays, they are like based on x86 architecture. So even if you don't have right now x86 computer, the information that you learn today is still like very useful for you in the future. So one of the important concepts first to understand is virtual memory. And now please just bear with me because I know this is very theoretical and it could be boring, but this is something we need for the exploitation, and it's not that difficult. If it's difficult, then it's just because I'm explaining it poorly, right? So if you don't understand something, just please ask me, and I will try to re-explain it as long as you guys understand it. Because I think if it is explained clearly, then you should be able to understand it. Okay, so what is a virtual memory? Does any one of you know? Like, I guess it's not a new thing for you. For example, I remember in architecture of computers, APO, right? It was in a bachelor degree. Like I had this class. So anyone wants to say what do you think a virtual memory is? Yeah. Yes, exactly. So yeah, perfect. So I will try to repeat it a little bit. So basically what we heard is that it's a process that it's an address space that belongs only to one process, and like other processes cannot access this space, right? Okay, here. Thank you for answering. Yeah, that is perfectly correct. So basically virtual memory is like a big chunk of address space, but it is related only to one process, right? So if you have one address in a process A, and then you access the same address in a process B, there's going to be something completely different, or you might not even like be able to access it. It belongs to a different process. Then there is some memory management unit that is translating these virtual addresses to physical addresses, but we don't really care about that right now because we are exploiting the binaries in, let's say, the user space or like in the virtual memory context. And this virtual memory separation, like per process, is very important, especially as, sorry, your name was? Jan? Jan. Thank you. As Jan said, it's from like it's important from a security perspective, right? Because there's like a process isolation. So one process cannot access data of some other process because that would be bad, right? You could read basically any data you want. So you don't want to allow that. Okay, so here we can see how virtual memory is approximately separated. So there are some sections. So there is a section with operating system stuff, with environment variables, then you have stack, then you have heap, data, and program. So what we care most in this class is only here the stack section, all right? We don't care basically about anything else. Does any one of you remember what stack is used for? Like, why do we have stack? And why is it called stack? Someone? I have a whistle. Yeah, exactly. Pretty nice. You want a whistle? Yeah, that was like a movie scene, right? Okay, sorry.
Just want a little
Sorry. Please wash it before you use it. Yeah, so basically what our colleague said, that it's used for local variables. That is perfectly correct. So there are local variables on stack. And why is it called stack? Is that it works as a stack data structure, right? So the first, the last thing you put in is the first thing that goes out. So it's last in, first out data structure. What is very important for you to notice in this diagram is that stack is growing downwards, okay? It grows towards the 0 memory address. What it means is that if you want to make the stack a little bit bigger, you want to allocate some memory on the stack for your local variables, all you need to do is that you subtract some value from this stack pointer. So stack pointer is a registry that is always pointing to the end of the stack, all right? Always is going to be pointing to the last value on the stack. And that means if you want to allocate some memory on the stack, you just subtract from this value, right? Because it means you basically made the stack a bit bigger, and that's why you can use the memory on the stack for your local variables or whatever you want. And when I say you, like, I don't mean you, like, this is doing compiler for you, right? But yeah, for us to understand it, I'm saying it like this. All right, so this is basically what I just said. And I'm going to mention 2 more registries that are important. So one of them is the stack pointer. I said it always points to the top of the stack. Then we have also RBP, which is base pointer. Base pointer always points to the start of the stack frame. So what is a stack frame? So it's when you enter a function, you allocate memory on the stack for your local variables, all right? But you need to be able to reference them. So you need to be able to access them. So base pointer points to the stack address when the function began. So basically you can say, okay, so base pointer -4, there's one local variable. Base pointer -8, there's another local variable. So you can think about it as like a starting point on the stack of a function. If this was not clear enough, like in a moment, I'm gonna show you some diagrams and hopefully it will be more clear. And the last registry I want to talk about is instruction pointer. Instruction pointer is very important because all it does, it's always pointing to the next instruction that is going to be executed, okay? So, for example, if you want to jump to another instruction, what it means is that you just put address of the instruction to the instruction pointer. Like instruction pointer always points to the next instruction, and usually when like usual code is executed, then it's like one instruction is executed, and instruction pointer is incremented. So it points to another instruction, and so on, and so on, and so on. But maybe you have a branch, and that you want to jump to some other instruction, so you just overwrite the instruction pointer. Again, very soon I'm going to show you a diagram, and hopefully it will be a bit more clear. But before that, I also need to talk about 2 instructions that are related to manipulation of the stack. It's a push and pop. And as I said, stack works like a stack data structure, right? If you have a stack data structure in your program or anywhere, like probably it has like a push and pop interface. So that's the same stuff you have here. So one thing that you can do with a stack is that you push some value on the stack. What this does when you push a value on the stack is that the value is going to be put on the stack, and you subtract a value from stack pointer, right? Because I said stack pointer always points to the end of the stack, and if you just put something on the stack, you made the stack bigger, right? That's why you subtract from stack pointer to enlarge the stack a little bit. And then you have completely the same but opposite, which is a pop instruction, and that's just putting a value from the stack into your registry, and it increments the stack pointer because you made the stack smaller, right? You took something from the stack, you made it smaller, so you increment the stack pointer, which always, as I said, points to the end of the stack. Okay, so that is all from like a hard theory. Now let me show you some diagrams, what is actually happening in assembly. I promise it's not going to be that difficult. The first concept that we need to talk about is how you call a function in assembly. So it's very similar as when you call a function, for example, in C language or anywhere else. Like if you are programming in some higher level language, you are using functions, right? Those are translated also to functions in assembly. So in assembly, you have a call instruction, and then you basically have just an address where the function is located. That's all. And what is happening is shown in this diagram, okay? So you have state before calling a function that is here on the left side, that is number 1. And then you have a state after calling a function here. This is the right side, number 2. So you can see that before you call a function, your instruction pointer points to an instruction call, okay, right? As I said, instruction pointer always points to next instruction that is going to be executed. So in this case, this instruction is going to be executed. So we want to call a function that is at this blue address FF120, all right? So what happens is that we put this address into the instruction pointer here on the right side. You can see that instruction pointer now points where the function is. And also, this next instruction that was after the call is put on the stack. Here, can you see that the stack pointer is moved because we made the stack bigger, and we put the next instruction on the stack. Does any one of you have idea why we did this? Why is the next instruction after the call put on the stack? Yes, exactly. So the answer was because we need to remember like where we were before. So this is basically a return address, right? This is after the function ends. This is where we are going to continue with our execution. Because as I said, it's as in any other language like Java, Python, Go, C, whatever. If you call a function and the function ends correctly, you just continue going, right? So that's the same you want to do here. So after this call function ends, you just want to keep going. But you need to remember where you were before, right? So the next instruction after the call, you put it on the stack. So later you can pop it and you can like continue going. What this means is that calling a function is just equivalent just to these two instructions. It's nothing else. So you just store on the stack the instruction pointer. You just store the return address, and then you jump to the function. All right, just basically these. It's equivalent. Like you could say it's a syntax sugar in assembly. So what is interesting to notice here is that if you realize it, you are putting a return address on the stack, but on the stack you put also local variables, right? So maybe you are putting user input on the stack, but the stack also has a return address, right? So if you know where I'm going, like maybe it's dangerous, right? Because if you can manipulate with, or if user can manipulate with the stack, maybe he can manipulate with the return address as well, and then he can make you as a program do whatever the attacker wants. But we'll get to that a bit later. All right, so and then another diagram. This is what happens when you want to leave a function. So again, for example, in C, you just type return, right? And maybe you return some value or not, but you don't have to, I think, in C. Sorry, it's a long time. But you just type return, and that's it. So in assembly, you have a ret instruction that basically does the same. And again, you can see here that on the left side, we have that instruction pointer points to the return instruction. So we want to return from a function. So all what this does is just we pop the return value that we put on the stack before into the instruction pointer. See, it's just like one operation. If we want to return from a function, we just pop a value from the stack into the instruction pointer, and show goes on, right? We just continue executing the instructions before we call the function. Does it make sense? Yeah, I see someone nodding. Is there someone lost?
Yeah, anyone lost? Remember, it's important. You're here to learn.
But this is the last theoretical part. Like after this, we go to we will start writing exploits. So if you have some questions, just ask me. I will try to explain again. So who is not lost? Okay, quite few. I like it. Okay, perfect. Thank you. Okay, so that's basically all from the theory. Now we are going to be talking about stack buffer overflow. So that's the vulnerability that we will be focusing most on today's class. So a bit of the background. So first public mention of stack buffer overflow was in 1996. It was in the e-zine called Frag. I don't know if you know it, but it still exists. It looks like this. It's one of the old school e-zines for hackers where you could find all sorts of interesting information. Interesting is that it still is functioning. So there is like a new release from 2024, right? I think. So you can read some new articles from hackers, or you can read even like old articles from 80s or 90s, what people like freaking and stuff like that. It's very interesting.
Before Google, this is how people learn stuff, right? You went to Frag, and then you read how they did buffer overflow, and then you went home and then just try stuff. So this is still, there is a great source of how things were like being done in like 40 years ago, which still works today. A lot of this stuff, as Martin is gonna show, is still working. So this is kind of a great source of knowledge.
Yeah, right. This is our history. Yeah, so you can read it. There are some like ASCII diagrams explaining of how they are exploiting it. Very cool. And maybe more interesting is, as Vero said, that even though this was first mentioned in 1996, like we are still hearing about it nowadays, right? Even nowadays, you can hear about stack buffer overflow in some software, and that attackers can exploit it. So, like, why, right? It's 2024 now. It's like almost 30 years. And still hearing about it, so like, can we fix it finally or not? Well, the question is not really, right? Because it's not really a bug. It's like it's inherent to the design of computers, how we use it nowadays, of like processors and operating systems. So we can try to minimize the probability of this happening. So for example, you can use like a memory safe languages, right? You can use like Java, Python, something higher level, or you can use like low level but memory safe, something like Rust. But still, it doesn't mean it's not gonna happen, right? Because there can be a bug in the compiler, there can be a bug in the interpreter, there can be a bug in the operating system or in the Java virtual machine or anywhere. Like, still, even if you use this high-level language, at the end of the day, it's going to be run in the assembly, as I showed you, on the same processor, and the bugs can still be there, right? So we can only try not to do these bugs and these vulnerabilities, but I'm pretty sure it's gonna keep happening. And just to showcase to you that it's still happening, so for example, last month, in October 2024, there was a high vulnerability in Adobe software. So there was a stack buffer overflow, which allowed attackers to remote code execution if you opened attackers provided file in Adobe Animate. Or last year, there was a famous, like a lot of people were talking about it. It was heap buffer overflow vulnerability in curl. Maybe you remember it. And many more you could find, not only these ones, but I'm sure even from maybe last month, you could find a lot of them. All right, so let's just see in practice what the stack buffer overflow is, right? And how we can exploit it. So during this class, we all are going to be working in a machine called Exploit Lab, where you can SSH. So please, all of you, if you can just SSH in there right now. The Exploit Lab is going to be the same for online students and for CTU students. The only difference is how you connect in. So for online students, please can you open or fire up Strato CyberLab, click on Start Class 8. I'm gonna do the same. So here I have my Strato CyberLab. I'm gonna start class 8. I'm gonna make it a bit bigger. And then you can SSH to this IP address with password admin. Okay, see, I'm there, perfect. And similar stuff I want from you guys here, please. If you can SSH to this IP address from your container that you have, but do not use root, but please use a user underscore your number, and you can find your number in the output of a hostname command. So I'm gonna show you the same. I'm gonna also connect. Oh, let me enter this. So this is my container, the same as you have. I type hostname. I see that my user is user 5. Let me connect in. Changing the number. Password is admin, and I'm there. Okay, and I'm sure you guys just noticed that you all share the same password and you know the other users. Just please don't log into like users of your schoolmates and mess with them. Just use your own ones and everything's gonna be nice. So after online students and here CTU students, after you log in, you all should have an equivalent machine and you all should see the same. So from now on, like I'm gonna be showing just one scenario, and hopefully it will work for all of us equally. Okay, are you connected without issues? Was it working? Okay, I see some nodding, perfect. Okay, so we can move on to our first example. We are going to be working with files that are stored in this directory, which is a /data binary exploit class. You can see there is a couple directories. So first, just copy please the stack0 directory to your home and change the directory there. And after you do that, you will see two files. So one C source code, which looks like this. I have it also in the document in here. Okay, so this is the source code. You can see what it does. Again, it's quite easy. You have just one main function. We define one local variable, which is integer. Then we define second local variable, which is a buffer. It's an array of characters with a static size 64 bytes. Then we assign value 0 to the integer variable. We read user input, and then we compare whether the integer variable is still 0. And if it's not, we print access granted. So this is what we want. We want to exploit the binary and make it print this string, all right? Of course, this is not advantageous for you right now, but you can imagine that there is no access granted. There can be anything else that is working for your benefit, right? Like leaking some keys, installing backdoors, whatever. For us, this is right now just a placeholder, and if we see access granted, we successfully exploited the binary. So what the directory also has is a makefile. This is the content, very easy one. There's just a GCC command without any special flags. So we will produce like a standard binary, like without doing anything special. So we can use the makefile with the command make. Okay, again, we see some warning, but hey, who cares? And the question is, what is wrong with the code? Like, if there is something wrong with it, but probably is, right? Otherwise, I would not ask. So what do you think, guys? Like, do you see directly what you should do in order to print the access granted string? Or like, before I do that, I can show you that actually I can run what we compiled. Now it expects user input, hello world. Okay, access denied, did not work. So do you have an idea what I should do? Or if you see the source code, is there something wrong with the source code? Yeah? 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 Yes, exactly. So what we just heard is that maybe we can write more characters and overwrite the 0 value. But the question is, why? Why can we do that? Like, what line in the C code is allowing us to do that? Yeah, exactly. Yeah, exactly. Basically, that's true. So it's this line. It's the gets buffer, right? So this function is dangerous. You could see it here when we compile the application. Warning: the gets function is dangerous and should not be used. But whatever. And the reason is that it doesn't check like what it should read, right? So it reads user input until it reaches new line. But the new line can be like after a million bytes, right? Like you as a programmer don't know what the user is going to provide you, so you should always sanitize user inputs. You probably heard it. Right now you will see what can happen if you don't do that. So in theory, like what should I give to the binary to print the access granted? So we heard maybe I can give there like more bytes, right? So how many? What do you think? Like what is the input exactly that is going to print the access granted? Actually, to make it a bit visual for you, we have this diagram that shows how the stack looks like when we are in the function, okay? So as we said, when you enter a function, and it applies also for the main C function, you put a return address on the stack, right? We already said that, so you can see there's the return address on the stack, which is basically just the old instruction pointer. Then what you also do, like usually after the return address, there is also a base pointer. And it's because, as I said, when you enter a function, you need to update the base pointer, right? So like for the current stack frame. So what you do is that you store the old value of a base pointer on the stack so you can later pop it. It's basically like a backup. We don't really care about it right now. It's just for you to understand that there is also some base pointer value on the stack. Not that much interesting for us right now. And then you have the local variables. So you see, okay, we have the modified variable with the value 0. And then we have the buffer, which is 64 bytes. It starts here. And the values can be random because we didn't initialize it to anything, right? Whatever is in the virtual memory right now, it's there, but we don't care. So now when you see this, like, how many bytes do you think I should provide to the binary to print the access granted? Like to override this modified variable. Any idea? Any guess? No? Well, an integer in C, like how big is it? Yeah, exactly. 4 bytes, good. I think so as well, at least. So and then you have 64 bytes of the buffer. So in theory, right, if you put 68 bytes, you will fill the buffer, and then you will also put 4 more bytes that should, in theory, at least based on this diagram, overwrite the 0, right? Make sense? Okay, so we can try that. For the exploits, I'm going to be using Python. At first here from the command line, because what you can do is, for example, in Python you can execute code like this. So for example, this will print number 1, or I can print character A, or I can print character 8 68 times, and I get it here, right? It's a convenient tool. I use it like this. So maybe we can pipe these characters into the binary that we produced, right? So in theory, if I run this, we should see access granted. And we don't, because in binary exploitation, nothing is that easy as it looks like. So there is one more thing that we need to bypass. But first, let's understand why this is not working, right? So, okay, so let's just go into the binary and try to see why this was not working. For that, we are going to be using GDB. GDB stands for GNU debugger, and it's basically, if you have ever used any other debugger, for example, in some IntelliJ software or somewhere where you put breakpoints and you see variables, it's exactly this. It's just a bit low level because you can see also registries and stuff like that. But before we run GDB, please can you just put this line that you see right here into this file .gdb init in your home directory. So what this does is that any command that you put in this file will be executed after you start GDB. And we are doing this before by default. If you disassemble a function in GDB, it's going to use AT-AT syntax, which me, honestly, I don't like, and I prefer Intel syntax. And I don't really understand why the default one is AT-AT, because if you read any blog post or article online or anywhere, like I think majority of the people, they use Intel syntax. So this is just a matter of preference. I'm going to put it there as well. Okay, I got it already here because of testing. So after we do that, you can just load the binary into the GDB like this, and then we can disassemble the main function to see what is happening. Okay, can you see it? Don't worry, this might look scary, but we are not going to go through all of it. We are interested only in the top 3 lines. So these 2 lines, you can say that these are like basically introduction to any function. It's not really related to our implementation. It's almost always going to be there. Right now, we can skip it. Important line is this 3rd one. So you can see that there is an instruction, and what it does is that it subtracts 50 in hexadecimal from stack pointer. So as I said, when you want to allocate memory on the stack, you just subtract from a stack pointer, right? So, and this is what exactly what is happening. So after we enter the function, we are allocated memory on the stack for the local variables. And in this case, we are allocated 50 in hexadecimal, which if we convert it to decimal, it's 80. So we allocated 80 bytes on the stack. Not 68 as we thought, right? In the diagram here, we thought that there is the buffer and just the modified variable, which we thought was 68, but in reality, there is 80. The reason is that some architectures, because of like performance and optimizations, they want the stack to be aligned, and the compiler knows it. So the compiler decided, okay, let's not allocate 68 bytes, but we are going to allocate 80 bytes. That's all, like no more magic is there. So after we have this knowledge, we can actually update our exploit. Yeah. 80? Yeah, okay, so here the values that you usually see here in the GDB are in hexadecimal format. So we subtract 50, but 50 in hexadecimal. So if you just translate it to decimal, it's 80 probably. Yeah. Yeah, so we can leave GDB with the command Q. And now I can try to update our exploit and put 80 bytes, and pipe it into the main. And voila, see, access granted. We smashed our first stack, and this is our first stack buffer overflow exploit. Very easy, right? It's just one print, you pipe it into a binary, and you achieve what you wanted. Did it work for you? Yeah, nice. So, like a brain food is, what would happen if I put like more? What if I do 8,000? What do you think? Will it work as well? Like, will I see access granted or access denied or something else? Do you have like a guess? Yeah, you can try and tell me. That's also good. Like, that's how you learn. Exactly. Yeah, exactly. So what we heard is that we would probably overwrite the return address, right? If you see the diagram again, we would just keep writing like this, up, and wherever on the stack. But during this process, we will also overwrite the return address. So after the main function ends, we will jump to like a rubbish instruction or like invalid instruction that is not working. And probably we will mess up the binary and it will crash, right? So let's see. Yeah. So it crashed completely. But if I do, for example, just like 200, it crashed differently, right? So it depends like how much you overflow the buffer. Maybe like you overwrite too many important like variables. But in this case, what happened is that you also received access granted, right? So the main function finished successfully because during this process you also overrode the variable, the local variable. So you still got access granted, but then the application crashed. It really depends what is your goal. Like maybe this is enough for you. Like you are interested only in access granted, but sometimes you might wanna have the application running like even after like your exploit, right? Because maybe you change something and it will take effect in an hour. So you don't want to crash the application. You want to make it still running. All right, so that was our first exploit. Now the question is if we can like defend against this, like if we can make this not happen. Like one answer is yes, like don't write vulnerable code. But I guess that's not gonna happen. So the other answer is no, we really cannot. There is no like operating system or compiler protection that would protect you against this. Like there are other protections, we are going to talk about them in a while. But if you are overflowing like local buffer and overwriting other local variables, like there is no check like that would catch this. And yeah, at least if you use like a standard compilers like GCC, CLang, they are not gonna notice. All right, so I think I have a good time. I'm a bit faster than I expected. We can have maybe. Okay, I'm gonna move a break like in 10 minutes. We can start with binary protections. So as I said, there is no protection against this specific vulnerability that we saw in this C code, but there are other protections like coming from the operating system and compiler. So let me just mention some of them before we continue, because we are going to like be trying to bypass them or use them in our next exploits. So the first one is PI. That stands for position independent executables. This is enabled by default. So for example, when we run this binary, it was compiled with position independent executables. And what it means that every time the binary is run, the code of the binary is loaded to a different address in virtual memory. Okay, so an attacker cannot assume where the code of the binary is located. For example, the attacker would like to change some global variable of the binary or something. In order to do that, he needs to know where the variable is, right? But this essentially forbids you from doing that, because every time you run the binary, it's like on a different place in the virtual memory. You can disable it, for example, for testing purposes. In GCC, it's with this no-pi option. But again, this is not like an ultimate protection. You can bypass it. For example, if the binary has like other vulnerability that allows you to leak like addresses internal, because there is some other bug, can be whatever, then you can actually leak the address where the binary is loaded and then use it in your exploit, right? So this is good, but it's not bulletproof. And another protection, and these are very interesting in my opinion, are stack canaries. Have you heard about it? Yes, nice. Do you want to tell us? No?
goes something like
Yeah. You can try to say the same again for online people, but you were basically correct.
Sure. Hi, online people. So stack canary is a thing in the stack which you place there before you run the program, and you check the stack again, and if it's the same, it runs normally. However, if it got overwritten, the program doesn't run, something like that.
Yeah, you're almost correct. Thank you. Here's a whistle for you. So let me just say it again. So when you compile a binary with the stack canaries, so what happens is that when the binary is run and it's loaded into the memory, there is a secret value generated by the program. It's unique per the runtime. And every time you enter function, you put this value on the stack. And every time you leave a function, you check that the value is still on the stack and it's not corrupted. It's the original value that you put there and it's still there, right? Because if it's not there, it means the stack was smashed and probably even the return address was smashed, and probably there is some funky business going on and you don't want to continue running. There is something weird, either a bug in the kernel or an attack is going on. So in that case, if this happens, you just terminate the application and you say, yeah, that's it. And yeah, I think this one is very interesting. Again, it's not a bulletproof, because what you can do, if you have, as I said, again, like a different vulnerability in a binary that allows you to leak values from the stack, for example, then you can read the value of a canary, right? And there's only one canary value for the whole process. And then when you are smashing the stack, you can smash it in a way that you preserve the canary value, right? You put it back. And then the check succeeds, because when you are leaving the function checks, okay, was the canary changed? It was not, but you put there a correct value, right? You as an attacker. So the binary keeps running, even though like you pulled your attack. It's a bit more difficult to pull it off, because as I said, you need to somehow leak the value of a canary, but it's still happening in a wild. It's not a sci-fi. And also, what I found interesting, and I didn't know, so this protection is not enabled by default if you use GCC. So in order to enable it, you would use this GCC command line option. All right, so then the last but one protection is non-executable stack. Why do we need this, right? So as we see, you have multiple parts of virtual memory, and then you have like a different flags for different parts of virtual memory. So for example, you don't want all parts to be executable, right? Because some parts of virtual memory are only for data, not for code. The reason why it's like this is we are putting basically whatever we want on the stack, right? So in the previous example, I put just 8 characters, but I can put whatever I want. I can put also code, right? What if I put, instead of the A's, I put like an instructions, in like an assembly somehow, and then I override the return address and I jump to these instructions that I put there. Right? Basically, that's much more powerful, because I choose the code that is going to be running. I don't have to find the code that I want to run in the binary, but I put there the code and then I jump there. So in order to prevent this, by default, the stack is not executable. So if you do this, then the binary will be, or the kernel or binary, sorry, I don't know now, there will be like, okay, I'm not running this because the stack is not executable. So if you want me to jump to the stack addresses, it's gonna crash. Again, this is not bulletproof, because you can change if the section of the virtual memory is executable or not with just a simple syscall. So if you have another vulnerability in your binary that allows an attacker to run some syscalls or this syscall, he can make the stack executable, and then he can pull this attack. Of course, he needs to chain the vulnerabilities, right? Because first he needs to find vulnerability to make the syscall, and then he doing like the stack buffer overflow. But again, it's happening. Like it's a bit more difficult, but it's happening. Interesting page is this one, is the shellcodes database. So if you let me make this bigger. If you want to make this attack that I just described, you can use this page to find the payload for you. And there is a tons of it, like here. So for example, here you can see that we are focusing on x86 and 64 bits architecture, so all of these. And for example, you can see that there is a reverse TCP shell. So in the previous lectures, you saw reverse shells, right? That attacker can do a reverse shell. So I just open this. There is some explanation of the reverse shell, but then there is also like this, which is basically the whole reverse shell in x86 instructions. So when I'm overflowing the buffer, I just copy paste this. These are the instructions. I put it on the stack, and then I somehow need to manage to jump to these addresses, and it's done. Like I don't need to do anything else. And yeah, you can find many different payloads here. For example, if you want to execute bin shell, here you even have like the whole source code. Yeah. So you just copy paste this basically, then you jump to these instructions, and voila, you are running the code that you like injected yourself. Did it make sense? No questions so far? Okay, so then last protection before we again get our hands on is another interesting one, which is ASLR, which stands for Address Space Layout Randomization. And so what this basically means is that by default, and it's I think all operating systems are doing it right now, by default when you run any program or process or binary, the sections of the virtual memory are randomized. Okay, so the stack starts at a different address, like the program starts at a different address, and everything starts at a different address. Again, it's so that the attacker cannot assume where anything is. Like shared libraries, stack, heap, everything is in a different, it has like a different offset, let's say, right? So you cannot make any assumption where it is. Okay, so now let me show you this tool, which is called a checksec. And what it does is that it shows you what protections are enabled on like a tool or a binary or whatever that you put there. So we can use the binary that we compiled for the previous example. Okay, and in here you can see that, oh, maybe it's hard to see, but if I make it like this, okay. So the binary that we produced has no canaries. As I said, it's disabled by default. I don't know why, or like, yeah, I guess this is how it is. Then also the stack is not executable, and the position independent executable, the first protection I mentioned, is enabled. Then you have also some others that I didn't mention, but for us, these three are most important ones. All right, I have prepared for you one more demo just to showcase these protections for you. It's stored in the directory demo0, so please copy this again to your home directory. Now change the directory, and in here you can see one C source code. Very simple one. It looks just only like this. We just create one local variable, and then we print address of this variable. Then we print address of a foo function, and foo function is defined right here, so it's a local function. And then we print, oh, sorry, what happened? Okay, and then we print address of a system function. This function is implemented in the libc shared library, which is loaded like here at the top. So it's it lives in a shared library that is loaded during the runtime of the process. There is also a makefile that is gonna produce us two binaries. You can see one normal one, just GCC without any special flags, and then one more binary that's using this NoPy flag, which I said it's only, we saw it, sorry, here. It's this flag. It disables the position independent executables. All right, so let's use the make file. Okay, this time no warnings, right? Good. And we have two binaries. This is how, okay, here. This is how we are going to run it. We are going to use a watch command. This is very useful. If you don't know it, what it does is that you just give it a command, and then you just tell it like how often it should rerun the command. So in this case, it's going to run the main binary like every second. Okay. Okay, here in the top right corner, right here, you can see that the time is updated every second. So the binary is rerun every second. And in the middle, you can see the output of the binary. So now we are running the default, let's say default binary, like compiled with the default GCC options. And you can see that everything is changing, right? All the addresses. That's what I said, that all operating systems nowadays are doing the ASLR, so which is the address space layout randomization. So that's why every time like a stack is created somewhere else, like the binary is loaded somewhere else, and the shared libraries are also loaded somewhere else, right? You should see the same. Everything should be changing. Yeah.
We have a question from the internet,
Yeah.
I'd say. Sorry. Once a binary has been analyzed, bypassing the ASLR is somewhat straightforward with pattern matching. Is there any goal this ASLR accomplishes that we are missing?
I don't know if I understand the question.
Do you want to read it?
Yeah, maybe.
Sorry.
Yeah. Okay, so the question says that the ASLR is somewhat straightforward with pattern matching. So I don't think it is, actually. It maybe is if you open a binary in GDB and you check where some stuff is loaded and you do it multiple times, you will see the same address. But the reason why you see the same address is because before GDB runs the binary for you, GDB disables ASLR. So you don't actually see randomized addresses in GDB. But then, as you can see, if you run the binary directly, like I am doing right now, then everything is changing. Like there is a pattern that, for example, here you still have like 7FF, right? The rest is changing, but still the rest is like there are too many options where it's gonna where the stack is going to be, so you cannot basically brute force all of it. Like I don't think it's computationally viable. Of course, it could be. Like for example, in the history, there were cases that like this implementation of ASLR is in the kernel, and of course, again, there can be bug in the kernel, right? And that's what has happened before. That like there was a few or a little entropy of randomness when this ASLR was implemented, and that's why you could guess like where each section of the virtual memory is going to be loaded. So yeah, you can do that. Maybe if you do, it's worth like a black hat because you bypass like a current implementation of kernel ASLR. But yeah, nowadays I believe that everything is possible, but it's not that straightforward, I would say. Okay, so this was the first binary, but we also produced a second one, which was compiled, as I can show you again, with this NoPy option. So what do you think will happen if I run it again? Like maybe you already did, so you know, right? Okay, let me just run it. We can talk about it. Okay, so now you can see that everything is changing except the foo function. So we disabled the position-independent executables, and I said what the position-independent executables is doing is that it allows loading the binary to different address, upon every execution. But the binary is only this, right? The other sections, like local variable, is on the stack. Stack is not a binary, so stack is still changing. System function, that is a shared library, that's a libc. It's some other library. It's in a different part of virtual memory, so it's also changing. So only the data that is coming from our binary is not changing. It's this one. Okay, we are going to be using this fact in a bit in the next exploit. So in the last demo is this one. So what this does is that this disables ASLR completely. So this is what GDB is doing for you when you are running a binary. It will disable ASLR, and then you can like play with the binary. So we will do it ourselves just to see what's happening. And see, nothing is happening. If you disable ASLR, addresses of everything are basically static. So you can make very strong assumptions as an attacker where something is stored in the process and then use it for your advantage. All right, I hope you saw the same results. Unfortunately, what I forgot to mention is that you might not see the same results if you are running this in StratoCyberLab, if you are having computer with other architecture than x86, for example, the latest MacBooks with ARM computers, because there is some emulation going on, and it does not implement all the features of x86 processor. So maybe you saw a bit different results. Sorry for that, but yeah, that's how computers work nowadays. All right, so I think we can make our first break right now, and after the break we will get our hands on, and from now on we will be only writing exploits and only exploiting. This was all for the theory, so don't worry, now it's gonna be more fun. Okay, see ya in 10 minutes, right? Yeah. Okay guys, I think we can continue. Let's write some some exploits. Let's type, yeah. All right, so we ended with some protections, like compiler protections and operating system protections. The ultimate protection that I can recommend to you is just, as I already said, is to write a secure code. But now we are going to be seeing some not that much secure code. So let's move to the next example that is located in the directory stack1. So again, please just copy it to your home directory. My shell died. Let me connect again. I have some issues. Yes, I will. Okay. Okay, I'm there. Okay, let's copy the stack1 to my home directory. Let's go there. And all right. So now you can see 3 files. Again, see source code. I have it again in the document. So it looks like this. It's a similar pattern as before. You can again see there's a 64 bytes long buffer. Then we read user input. But then we execute a function that is defined here in a local variable, right? So by default, if you run this application, actually I can do it. Again, I can use provided makefile to compile the application and run it. I can give it some input, and I receive access denied, right? Because there is, in the local variable, there is a failure function that we call, and it just prints access denied. But there is another function, which is called success, that prints access granted. But imagine that this function is doing like installing backdoor or whatever. So we want to execute this function. Very similar to what we saw before, with the only example that now we are not overwriting a local integer variable with whatever you wanted, right? We need to be precise. You need to put address of the success function so it is executed. One more file that you can see in the directory is Python template exploit file. This is how it looks like. So I prepared for you like a general structure for this first example, where you can only fill like these 2 lines. After you fill them, so what is happening is that we are putting some A characters. So, okay, so we want to fill the buffer, right? And then we want to put address of a function that we want to call to override the local variable, but we cannot just like we need to put it in a correct format, right? So for that we are using the struct.peg function. It's in the standard Python library. What this does is that the queue says that we want to output 64 bytes address and to respect the architecture of the computer, like to respect the byte order, right? It depends if your computer is little endian or big endian, like whether you type it like from left to right or right to left, right? So this is what it handles for us. You can use this command to see like what is the architecture of your computer. In here it's little endian, but we don't really care about that because the struct.peg command will do that for us. So what we need to do right now is just to find the address of a success function, right? Because that's the value that we want to put. Let me show the C code again. That's the value that we want to put into this local variable called FP function pointer, I guess. So for that we can use GDB again. So GDB is pretty powerful, and in this case pretty simple. You just load the binary, and then you just want to print information about the success function. So P as print. You can make these shortcuts in GDB. And see, I received address where the function is located. So in theory, I can use this address and use it. I hope you can see it. I could make it bigger and use it in our exploit. Like the question is if I can use it, right? Like, will this address be the same every time I run the application? Well, probably in a production, no. But you can see in our makefile that in this example, we compile the application with the NoPy option, which means that actually the randomization of program of the binary is disabled. So that's why this address is always going to be the same, right? If you remember before, in this demo example, I was running this pane NoPy, and the address of a foo function is still the same. See? Still the same. So that is what is happening right now in this example as well. That's why we can assume that the success function is still going to have the same address that we saw in GDB output. So let me go back. OK, we are here. So now we can try to write the exploit. So as you saw in the exploit, we need 2 values. We need the function address. I think we just found it. But then we also need the buffer size. This is like how many A's do we put there, right? So what do you think? How many A's do we put there? Or how do we find like how many A's we put there? So like we want to put exactly that many A's to reach where the function local variable is located on the stack, right? It's the same as we did before, like in the first example. We can actually for that use the GDB again in a completely the same way as before. Because if I do disassemble main, as we did in the previous example, again I see that there is 50 in hexadecimal bytes allocated on the stack. So the stack has the same size as before. So we can put like this many bytes on the stack. Does it make sense? Okay, let's try that then. Oh no. All right, so the buffer size, or like the size reserved for local variables on stack, is 50 in hexadecimal, so I can put it like this, because you can see that on this line we put -8, so we keep like the 8 bytes for the address of a success function. Does it make sense? Okay, so let me find the address of or let me print it again so I can copy it. Oh, I have some. I cannot type. I can. You just can't see it. Okay, that's weird. I can type blindly. This is a security feature. Okay, let me restart it. Sorry about that. Okay, I'm here. So let me go to the GDB and print the address of a success function. Let me copy it. And I can put it here into the placeholder where the function address is. See, I don't really put 8 bytes because that's what the struct.pack function is doing for us. So it's gonna check whether it's little endian or big endian, and it's gonna fill the zeros on one of the sides to exactly output 8 bytes. And we reserved like 8 bytes because we subtracted 8 here from this buffer size. So this, in theory, should be enough. I can try to run it. Okay, you can see there is some output. And if I pipe it to our binary, we got access granted. Ta-da! So just to show it again, this was the code. So we took address of this function, we overflow this buffer and put the address into this variable, which was run over here, and that's why we received access granted. Does it make sense? Do you have any questions about this example? Who is not lost? Nice. Pretty good. Okay, thank you. Let me see if I forgot about something. No? Okay, perfect. So now we can move to another example that is stored in the directory stack2. So again, please just copy the data to your home directory. Then I can go there and see the files. Okay, so what we have here. So there is again some C code. This time it's much less of a code there. So again, there is some buffer. Then we are reading user input, and that's all. We are not even printing anything, right? But there is this success function, right? So maybe that tells us what we want to do. But there is no other local variable on the stack that we would like to overwrite. Do you have an idea what we could do? Like, again, our goal is to execute this success function and to print access granted. Yes, exactly. So the answer was to rewrite the return address. That's exactly correct. Let me show you a diagram again of just to remind you how it looks like. So in this case, there is only 64 bytes buffer, like for local variables. There is no other local variable, right? And then before I said that usually you also put old RBP value after the return address. So we need to count that it's there. And then there is the return address, which maybe we can overwrite, right? So it's very similar, again, to the previous example. Just in this case, the success function, the address of a success function that we want to execute, we are not going to be putting it into a local variable that was right here, but we will try to put it here instead of the return address on top, right? That sounds easy, right? So we just maybe just change the noise that we output. Let's see. So again, I provided to you a template, Python template for the exploit. This time we need to fill also this code in the below. So it's not that easy for us. But again, we need to find, like, I guess some size, like how many bytes we need to put like as a noise, and then the address of a function that we want to execute. As usual, you can see a makefile that we can use to compile the application. So let me compile it. Again, warning, we don't care. And yes. So what would you do as first right now? Like, what do we need to find? It's written there, right? So I also didn't like to answer these questions that were too obvious. So maybe you don't want to answer them too. So we need to find the address of a success function, so we can actually put it as a return address, right? So as before, we can use GDB and just print the address of a success function. But note that the reason why we can do this is, again, if you look at the makefile, there is again the NoPy option, which allows us to do this. Otherwise, the address of a success function would be different upon every execution. But since like somebody put this there for us, we can actually assume the address is going to be constant. Okay, so let me load the binary again. And let's print the success function. And again, I have the address. So let me copy it, leave GDB, and put it into our exploit. Okay, now the question is, like, how many bytes I should put before I put the address of a success function, right? We need to find out, like, how big, or like how many bytes are allocated on the stack for local variables. And again, we can use the approach we used before. We can check in GDB how the main function looks like in assembly. So if I go to GDB and I do disassemble main, okay, now it's smaller because there's not that much code in our main function. But again, important line is this one. Yes, sorry, I guess you don't see it right very well, but it's 40 in hexadecimal. So in this case, we allocate only 40 in hexadecimal bytes on the stack. Before it was 80 in decimal, right? But it was because there were more local variables. Right now there is only the buffer, which has a size 64 bytes. And if you convert 40 in hexadecimal to decimal, then it's 64. Okay, so we use 64 bytes buffer in our C code, and that's exactly the number that is used by the compiler to allocate on the stack for us. So if I go back to the diagram, so on the stack we have exactly 64 bytes for local variables, so the diagram is correct. Then we have the old RBP value, right? And then the return address. So I think we have all the information, so we can try to finish the exploit. Let's just hope I won't make a mistake. So the size that we want to put there is that we have a 64 bytes buffer here, right? Then there is the old RBP value, which, because we are working in a 64-bit architecture, so it's an address, so it's 8 bytes. So it's 64 plus 8. And then we just put the function address. So basically this should be all in theory. So we will put some characters this many times. And then I will put, again, using struct.pack function that I explained before, the address of a success function like this. And this should be it in theory. Okay, let me try to execute this. Okay, see, I get some bytes without error, so that's positive. And if I pipe it, access granted, and segfault, yeah, that's like what we get. But we executed the access granted function. That's what we wanted, but we also received like a segmentation fault. Do you have an idea why? Yes, exactly, good. Yeah, so we override the return address, we jump to a function, but then the function that we jump to is also returning, right? But like it has like nowhere to return, but because like the stack is smashed, like there is no, we didn't prepare like a return address for the function where we jumped, right? In theory, we could do that. Maybe it would be a bit more work, but the way how we smashed the stack right now, it only executed the code we needed, but then the binary crashed. Yeah, exactly because of this. Good answer. Perfect. So let me see if I forgot something. Yeah, sorry, I'm jumping like this here. I think I mentioned all of this. Okay, I'm still a bit faster, so that's good. We will have more time for the return-oriented programming. Okay, so this was basically all for the like basic stack buffer overflow. Let me just do a small recap, because after this we will move to return-oriented programming, which might seem complex if you didn't really understand everything in these previous examples, but I will hopefully try to explain it like goodly. So what we did is that we managed to override the return address and to jump to some function, right? But we jumped only to functions that didn't take any arguments, right? If you see again this code, it would not be that easy if a success function was taking some argument, right? Because we just jumped there, but we didn't prepare the argument actually in assembly. So that would be a bit more difficult, but it's okay, we can work with that. Right now, we can just accept that we can execute any functions that take no arguments. Another brain food for you is like, can you think about what would happen if we override the return address with address of a return instruction? Let me show you again the diagram here. So what we did before is that we overrode this return address with address where our function is located, right? And what I mean function is located, I just mean instructions of a function. What if we put here address of return instruction? What would like happen? What do you think? Will the universe explode? Yes? Yeah, maybe. Well, it's just weird, right? So what we said, like in a theory in the beginning, is that what the return instruction does is that it only pops a value from the stack to instruction pointer, right? So if we put here address of return instruction, we will jump to that instruction, to the return instruction, so then return will get executed, which means we will pop another value from the stack, which is like somewhere here, right? And we will jump like to address that is here. Okay, this sounds like it's useless, right? Like why would I do this if I can jump directly to this address? But it's just good brain exercise to think about it, because we will use this just now in the next example. Because right now we move to return-oriented programming. Let me just go over the basic introduction, and then we can have a break. So some motivation for a return-oriented programming, or what it is that, as I said, we are able right now to execute functions that take no arguments, right? But usually that's not how, like, what you want. You want to execute functions that take arguments, because, for example, let's say you want to spawn a shell. So you need to give the shell argument to the system function. Or you want to execute something else, and that might take arguments. So you need to prepare the arguments. And in the beginning, in the theory section, I said that in x86 and 64-bit architecture, you pass arguments to functions through registries. So that means if you want to execute a function with arguments, you can jump to this function, but you need to prepare arguments in the registries before that. Because the function instructions, they assume the arguments are already in the registries. So that's why you need to prepare them. And to do this, we use this technique, which is called return-oriented programming. It's very cool. It might look intimidating, but I promise you it's not. So basically what return-oriented programming is that we take like a series of codes from the binary that we are exploiting, and we are chaining it together to achieve like the code that we want. So we need to set up the arguments, right? But maybe we need to set up more arguments. So that's like a lot of instructions. So you chain instructions and you execute them one by one to, for example, prepare the arguments in the registries, and then you jump to your target function. Let me show you, or like we will show you in a bit, but let me show you what you use in return-oriented programming. So I said you use a series of instructions which you chain together. One series of instructions is called a gadget. And a gadget can be whatever length and can be whatever instructions. For example, can be these two instructions, right? So it can be pop RDI and return. Why am I showing just this gadget? Is because the first argument is stored in the RDI, right? And to put something into the register, you can put this instruction. So if you do pop RDI, you take value from the stack and put it into the RDI, right? So this gadget is essentially preparing a first argument for whatever function that we want to call. Does it make sense, right? For now, this is very abstract, right? But it's gonna get practical. So to find these gadgets, or I can show you right now, like how many gadgets there are and how to find them. We can use a tool called Řepa. I think it's not installed in, it's installed in StratoCyberLab, but it should not be installed in your user_number environments in Exploit Lab. So if you can please install Řepa. I think it should be installed here in my shell, yeah. And then also please execute this command, which will just put the binary that you just installed into your path so you can execute it conveniently. So and you can use Řepa like this. You just give it some binary and it outputs you all the gadgets that it can find in the binary. So if I do, I'm just going to show you this, which date. Sorry. It just shows a path to the binary date. So I'm gonna put the path to the Řepa. Let me make it, I guess, bigger. Okay, so here you can see every line is a gadget. It's some gadget. You can see that, as I said, a gadget is a series of instructions. So every line is a series of instructions. For example, let me find some. These are quite complex ones, but for example, here you have a gadget that has only 3 instructions. It has some subtraction, some addition, and then return. Do you see some pattern in these instructions? Like, what is always there? I don't know if you can see it, but hopefully you can. Yes, exactly. So it doesn't have to, but majority of the gadgets, they have a return instruction at the end. So this return instructions at the end is that what allows us to chain the gadgets, right? The instructions. Because remember what I said like before the brain food, like what would happen if we override the return address of a function with return instruction? We would just pop another value from the stack and jump there, right? So actually, if we don't override the return address with the return instruction, but we override the return address with address of, for example, this gadget. Okay, let's assume we use this gadget, okay? And we override the return address with this address. That's the address where the gadget is located in the binary. So we will jump here. So this instruction will get executed, and then return instruction will get executed, which means we will pop another value from the stack and jump there, but maybe we prepared another gadget there, right? We prepared address of another gadget on the stack. And so now we jump to another gadget. And for example, we jump, I don't know, let's see another some small one. Okay, here. And we jump to this gadget. So what this gadget does is just, it pops a value from stack to this RSI, let me make it bigger, registry, and again, then it returns. And then maybe it jumps to another gadget that we prepared there, right? And like this, we can chain the gadgets, and we can actually execute a series of instructions that we want to achieve anything. And with this series of instructions, we can maybe set up all the arguments in all the registries, and then jump to our target function and execute whatever we want. Did it make sense? Who is not lost? Nice. Okay, it's less hands now. Do you want me to try to say this again? Someone? Yeah. Okay, let me try to go back. Here. So in the previous example, we overrode this return address with address of the success function. But what we can do is that we override this address with address of a, for example, let's simplify it, with address of a return instruction. So we jump to this return instruction, return is executed. What it means that return just takes another value from the stack and goes there. But maybe we prepared one more value on the stack here, and so now we will jump to this value. And maybe we prepared there like again just another return instruction. So we will jump to this return instruction, and that will again just pop a value from the stack, and maybe we prepared another value on the stack, right? So this is how we can chain the execution. But this would be useless, right? Because it's only returning and like only jumping from address to address. So you actually want to achieve something. So that's why you don't put address of only return instruction, but you put address of a gadget that is doing what you want. So you first need to think about, okay, what I need to do. So for example, I want to execute this function, some function. It takes 2 arguments. So I need to prepare 2 arguments in 2 registries. So I need to find gadget 1 that prepares 1 argument, for example, then gadget 2 that prepares 2nd argument, let's say, and then I put address of a function where I want to jump. And after the last gadget finishes, there is again, as you can see, there's again a return instruction. So it will pop the value of a function that we prepared on the stack, and it will jump there. So what has changed from a previous example is that, again, in the end, we will jump to the target function that we want, but the arguments will be prepared in the registries. And since the function assumes the arguments are prepared, everything is fine, and like the function goes on, and it does exactly what we wanted. Was it a bit more clear? Oh, yeah, thank you. I see some nodding. All right, so now we can try to actually do this in practice. So this was a theory. I have a demo for you prepared with exactly this functionality, but actually I think we can have a break now, and no, sorry. So let's go in with this demo, because then we move to fuzzing, so at least like you can have a break before we switch topics. Okay, so this demo is again prepared in the files in your exploit lab. So you can use this command again to copy the files to your home directory and change it. However, please note, this is for online students that are using Strata CyberLab, that this demo will probably not work for you if you have like computer with, for example, ARM processors, chips, like the latest Apple MacBooks, because Docker is using like a QEMU emulation to run these x86 binaries, and it doesn't implement all the syscalls and features of x86 like operating system, so something is not supported, and that's why probably this demo will not work for you. So sorry for that, but I hope like majority of you have x86 computers, so in that case everything should work the way I'm going to show it to you, even though it's in the Docker. So first, please disable ASLR. So for this whole demo, we are going to be working with disabled ASLR because it makes our life much easier. Like otherwise, I'm gonna talk about this at the end of the demo, like how we would proceed if the ASLR was not disabled. It would be much more difficult. But now to understand like what return-oriented programming means and how you can chain gadgets, we will disable the ASLR. So you can do it with this command. Basically nothing should change, but right now I should be in a new shell, in a new bash session that has ASLR disabled for all children processes. All right, so again, there is a C source code. Let's look at it. And it's only this. And maybe you remember this because it's the code I showed you in the motivation part in the beginning of the lecture. It seems like so long. And so now we actually get to this demo where you will be able to understand what was in the magic Python exploit script. You can see that there is again nothing. So from the previous example, you already know that we can overwrite the return address of a main function. But in this case, there is no function that we want to execute, right? There is no foo function with access granted string. And our goal is not to print access granted. Our goal is to get a shell. So we want to spawn a shell. How we are going to do that is that we want to execute a system function. System, that's like the name of the function, and it's implemented in the libc library. And in here you can see that we are actually including the libc, the shared library. So it's going to be somewhere in the process. We can actually maybe find it and jump to this system function. However, it's a bit more difficult because system function takes argument, exactly one argument, and we need to provide the command that is going to be executed. And since we want to spawn a shell, we want to provide a bin, like a /bin/sh string into the system function. So our goal is to execute a system function, but pass to it one argument. Again, you can see there is a makefile. There is one one GCC option which says no stack protector. This is just to be sure that the compiler doesn't put stack canaries, because as I said before, if there are stack canaries, we are not able to override the return address, right? Because smashing of the stack would be detected and the binary would terminate and we would not succeed. So again, to make it a little bit easier, we put this option here. So let's compile the application. Again, warning, we don't care. Okay. So this is one more time what I said, like our plan. So just to review it, we want to execute shell. Shell is executed with this command. This is what you would write in a C code. If you want to execute shell, you would just put this as a one line in your code, and you would spawn a shell. So it takes one argument. The first argument is passed in the RDY register. So we need to put address of this string into the RDY before we jump to the system function. Okay, so far so good. And maybe we can do this with this gadget, like a really small gadget with only 2 instructions. All it does is that it's popping a value from the stack into RDI and then continuing. So if we prepare address of this shell string on the stack, and then we execute this instruction, we will prepare the first argument. All right. Does it make sense? But now we have like a couple problems, right, to tackle, because in here, no, actually, sorry, let me go over this diagram. Hopefully this diagram will explain to you more what I'm talking about. So this is like our plan. Again, you can see on the left side, this is how the stack looks like. On the stack, there is a buffer, right? 64 bytes as before, nothing new. Sorry, did I? No, sorry, I jumped too far. Excuse me. So this is how the stack looks like. Again, 64 bytes buffer, then the RBP value as before, and then the return address. So we can override this buffer, then we can override the RBP value, and then maybe we can put the gadgets. And this is how we want to put the gadgets. So you can see we override the buffer with something random. Let's say we put just A characters. Then we override the RBP value again with something random. We don't care. And then the teal color is supposed to be a return address, right? But our plan is to put the address of this pop RDY gadget that I talked about. So if this address that we put there is going to be pointing somewhere in the binary, whatever, we don't care, could be anywhere, but somewhere where the pop RDI instruction is located and return instruction right after it. So we don't really care where this is. It just needs to like fill these requirements that it's pop RDY and there's return after it. Because after we return from the function, we will jump to this gadget, all right? Which will execute this pop RDI instruction. So what it's gonna do is that it's gonna pop this address that is next in line on the stack into the RDY register, which is the first argument. Then the execution continues. So we jump here, we go here to this instruction, which is return. As we said, return is only pointing value from the stack to instruction pointer. That means we look at the stack again. But in the stack, we prepared address of a system function. So that means we actually jump to the system function, but already the first argument is prepared in the RDY register. I might like give you a while to look at it. Can I make it bigger? I cannot. I can. Makes sense? So who is not lost? Perfect. Wow, a lot of you. I would be maybe lost. All right, so let's try to do it. So basically, all we need to do is to prepare the stack like this, right? So these are just like placeholders, so just some A's and some B's. We don't care. But then we need to find address of this gadget. Then we need to find address of this string. And then we need to find address of this system function. So basically, we have 3 tasks that we need to solve. And then we can craft our exploit. To make it easier, we will try to find all these 3 addresses in a libc shared library. So that's why the diagram looks like this. You can see that it's pointing into the libc here. I already prepared it like this. So if we are lucky, we will find this specific gadget in the libc shared library. And if we are lucky, we will find this string in the libc shared library, and we already know that system function is implemented in this library, so hopefully we will find it there as well. So first we need to find what libc shared library our binary is actually using. So for that we can use GDB again. So let's load the binary into the GDB. And at this point, the binary was loaded, but it was not run. So shared libraries are not loaded yet because the process doesn't know what libraries it should load. So we need to run the binary first, but we don't want it to finish. So we can put a breakpoint into the main function, just like this, very easy. I put 2 breakpoints. Okay, I guess it's okay. And then I can put run. So it's going to run the binary, and you can see breakpoint 1 reached. You can verify this by disassembling main. In here, you can see this arrow on the left side. So it means that that is the next instruction that is going to run if I continue execution of the binary. So this is basically where the instruction pointer register is pointing right now. So we truly reached the breakpoint. And now we can do info proc map to see all the loaded libraries. Okay, like this. So in here you can see that we are using libc shared library that has this path, and it's loaded to this address. And because we disabled ASLR, the randomization of the layout, we can assume that this address is going to be always the same. That's why we disabled it. Otherwise, this would be different every time, and our task would be much more difficult. Right now, we can use this address as like a starting address of a libc program. And what you can also notice here is this params column. So as I said before, different parts of virtual memory, they have flags, for example, that the stack is not executable. So in here you can see that this is just one libc shared library, right? But it's loaded into multiple sections of virtual memory, and that is because they have some different properties. So for example, just one of them is executable, so it's this one. So probably just this section has code inside. The other sections, they could have static global variables or some other variables and stuff like that. This is just a note. We don't really need to know that right now. So what we need to know is that we are using this shared library, and that it's loaded to this starting address. So I'm gonna note this address. I'm gonna leave GDB. I'm gonna go to my exploit Python again. You can see there's nothing, so we will write all of it on our own. Let me make it bigger for you. Okay, so we can see libc start address is this one. Okay, we just found it. So let's store it, and we can go on. Also, let me copy. Let me make it like this. Let me copy this. This is the name, or this is the path where the shared library is loaded, right? I can do ls here. Okay, it's there. So I will just put it here, so I can maybe use it later. Okay, so here you can see a screenshot of what I just did. And now let's just try to find these 3 addresses in the libc, right? So right now we found this file that is here on the right side, but we need to find these 3 addresses. So first, let's search for the system function. We can use this tool that is called readelf. It's reading elf executables. And if you can see the command that I just copied, it's the file that we found here. It's the same one. And we just grab system. Okay, and we found it. So we found that this is the address, in hexadecimal where the system function is located in the libc. Okay? So in order to reference this system function in our binary, we need to know where the libc is loaded. But we already did, right? That was the starting address that I noted down. So I can copy this basically offset, and I can do that the system function address is at libc start plus this one I just found, right? And I can remove the leading zeros because that's just a zeros. And this is where the system function should be. Okay, does it make sense? Because right now, with the previous command, we found where the system function is, but in the file, like in the shared library. But the shared library is loaded into the memory somewhere, so that's why we need to also add the start address of a libc. So that's just like libc start plus offset of a system function. Any questions for this part? No, perfect. So second part that we need to do is we need to find the bin shell string. Since we already know where the libc is loaded and that it is loaded, we can try to search for it in the libc library and maybe we'll be lucky. And for that you can use just a strings command. A strings command just outputs like a strings in a binary, and with these options you also output like a positions where the string is located in hexadecimal. So let me execute this. Okay, and see, since we see some output, it means that this string is actually located in the libc and we can use it. And we also got address where it is located in the libc shared library. Note that this is hexadecimal, not decimal, as it could look like. So again, I'm just going to copy this and put it into our function. And I can say that bin sh string address is again libc start plus this one in hexadecimal. That's why I put oh, sorry, not equal, thank you, plus. Okay, so I got like a second part. So let me go back to our plan here. So we got the address of a bin shell, we got the system function address. Now we only need to find this gadget. And as I said before, we can use the Ropper to find gadgets. And actually, Ropper can find you like a specific gadgets that you are looking for. So if you know what you want to do, you can just tell it to Ropper. And in our case, we know, right? Because we want to prepare the first argument, which is in the RDY register. And that's why we are searching for pop RDY. So we can use this command. It's basically the same as before. I just added this one argument at the end that we are searching for this instruction. Okay, something's going on. Okay, perfect. So now you can see that all the gadgets that we see, they have somewhere in the series of instructions there is pop RDY. But we don't care about like other instructions, so we care only about this gadget. We are lucky because it's there. If it's not there, we would have to get creative somehow. But since it's there and it's exactly what we need, I can just copy this address, which is again offset of the gadget inside the libc shared library. So and I can note it down again. So this is pop RDY gadget address, and that's again libc start plus this. Without, I can remove zeros, and this is it. Save it. Let me go back to our plan. Okay, so we should have everything, right? Right now, in theory, we should be able to create our exploit. So let's try to finish it. So we need to first fill this buffer, right? So that's 64 bytes. So I can put, for example, A 64 times. Then I need to overwrite this old RBP values. So it's a pointer, so that's 8 bytes. So I'm gonna put, for example, B's now 8 times. And now let's start overwriting the return address. So first we overwrite the return address with the gadget. Again, I'm gonna use the strec.pack function, so it does all the handling of the format for us. And first I put pop RDI gadget address. After that, I want to put address of a bin shell. So let me just copy this. And here I put bin shell string address. And I see I have a typo here. And last one, I put address of a system function. Like this. To the end, I put a new line because, as I said, the gets function that we have in our binary, it's reading input until it reaches a new line. So that's why I put a new line. And that should be it. Then we just print it to the standard output. Let me see if it's working. Okay, it's doing something. And maybe I can just pipe it to, where is it? Yeah, I don't have it here. I don't want to scroll too much to spoil it to you. But if I just pipe it to the binary that we have, it's segfault. Ta-da! So, yeah, as I said, nothing is as easy as it looks like. So this is, we are not there yet. And the issue is, I'm gonna tell you, I'm gonna explain straight away to you. Wait. Yeah, it's the same issue we already encountered, and it's that the stack needs to be aligned. Like some functions, they expect the stack to be aligned, and right now we just put like a lot of weird stuff. Where is it here? We put a lot of weird stuff on the stack, right? So the probability that it is aligned, like it needs to be aligned to 16 bytes, and since we are putting like addresses, and one address has 8 bytes, then I'd say it's like 50% chance that it's aligned or not. In this case, maybe it's not aligned, or maybe there's some other issue. We will see. So our goal is to align this. Do you have like an idea how we could align this? Like maybe we can put something more on the stack so it's aligned, but like, can you think of something we can put there to actually preserve this behavior that we like specifically crafted and make it bigger? No. I have a dinosaur.
Glow in the dark.
It's glowing in the dark. Yeah, we can turn off the lights later. Sure. The exploit? Yeah. Let me make it a bit bigger. Yeah. We just want to put something more. So we want to put more values on the stack, probably 8 bytes, because it needs to be aligned to 16 bytes. And if you think about it, right now we are putting 64 bytes, that is divisible by 8. We put 8 divisible by 8, and then we put addresses. And since we are in 64 bits system, this struct.pack with Q argument will also output 8 bytes. So all of this is divisible by 8, but we need the stack to be aligned to 16. So probably we are missing 8 bytes. And we want to put something. If you think about it, we want to put something so we actually keep this gadget or some gadget at this return address, right? Because this, we cannot move this. This is the address that is going to be popped into the instruction pointer. This is where we are going to jump. Okay, so I might give you a hint. I mentioned it a little bit. Oh, yeah? Yeah, you're going a good direction. Yeah, yeah, exactly. So we need something like nop, right? But like, so sorry, for the online students, so what your colleague said is that we need to put something like nop. We need to put like empty instruction. We need to put something that like, that does nothing, but it's still there, so the stack is aligned, right? Yeah? Exactly, perfect. Yeah, that's the correct answer. Yeah, very nice. Good job. So what we just heard is to put address of a return function, right? Did you meant it, right? So we can maybe find another gadget that is only return instruction, nothing else. So as I said before, right? Maybe before I was saying that maybe we can override. Oh yeah, thank you. Maybe we can override the return address with address of only return instruction. But I said that would make no sense, right? Nothing would be happening. We would just be moving on the stack a little bit like further. So, but that's exactly what we need right now, right? Because if we put a return gadget in front of this teal gadget, like, I mean, in between this BB and this blue gadget, then we will put like a nop instruction, because there's going to be address of a return instruction. We will jump there. You can imagine that it's there's arrow like here, right? To this red. What it does is it just pops next value from the stack, which is our gadget right now and our whole chain of instructions that we want to execute. Very nice. So let's try to do that. So we need to find this gadget, right? So let me just, I think we can search for red. Let's see, maybe searching for red is the same as searching for nothing. Like, I don't know. Okay, the duplication. Yeah.
Question from the internet. Isn't there a tool or something to detect this alignment?
Okay, good question. I don't know. I don't know any tool like this. It also depends on the architecture, right? Maybe it's not enforced, so the tool would have to respect the architecture. I don't know that. Like there are like a couple of tools to help you with this like return-oriented programming and to chain the gadgets. But honestly, I've never really used them. So I can try to look at it and maybe reply later. But right now, I don't know. Okay, so this is our result. Okay, see, and for example, right here, there is a gadget that is only return. Like it does nothing else. So that's pretty good for us. So let's just copy it. Let me put it here. So this is just red gadget. Again, I search in the libc shared library. So I need to add it to the start, remove leading zeros, and that is it. And as you can see here, I need to put it in between the BBBs and the blue ones. So I just put it here. Return gadget. So let's see if it's still doing something. It does not, but okay, it still does not. Yeah, let's remove this. Okay, so it's working, like it's outputting something. Now we can try to pipe it into our binary. So who thinks it's gonna work? Too bad. But now we are almost there. What is happening right now is that if you use this approach, like you are closing the standard input, right? But we are trying to spawn a shell, but you need to interact with the shell, right? You need to give commands to the shell. So you want the input of the standard input of the shell to be still opened, and that's why I used that trick in the beginning of the class that I executed the exploit like this. Let me just put it into a comment, because I don't know if you know, but if you just run cat without anything, do you know what's going to happen? Now it's just going to echo everything back to me. Right? So whatever I put there, it goes back to the standard output. So that's what we wanted in this case, because first we are going to output our payload, and then whatever we type is going to be replied back and put to the binary, which in theory should be shell. So who thinks it's going to work? Ah, ta-da! Return-oriented programming in action. Now you can do whatever. Hello from the other side. Cool, so we managed. Did any one of you manage as well? So I think if you are using in StratoCyberLab, both there and the container that you guys are using, this exploit that I just wrote is located here in the document as well. It should be one-to-one if I didn't make any mistake. No, sorry, this is the one before we put the return gadget, but this one. So if you didn't manage to follow what I was doing, you can just try to copy paste this and then like look at it and try to spawn the shell. By the way, if it's not working for you, just don't remember to disable the ASLR. There was the command in the beginning of the demo. You need to disable the ASLR, because let me show you again. If I do exit, okay, let me connect there. I just connected to the SSH, so I did not disable ASLR. And now if I do the same, it's not working, right? And this is because the ASLR is not disabled. Now I can do just that r-bash, ASLR disabled. Copy the command. Okay, and it's working. See? So that's why we disabled the ASLR. And yeah, honestly, it was quite complex to pull this attack off, right? But still, we helped ourselves a lot, because so first we disabled the stack canaries in the makefile. That's one thing, and the second thing is that we disabled ASLR. In production, when you are, for example, the attacker, and you would like to pull this attack off, you need to somehow bypass these two protections. It's not impossible, it's just a bit more difficult. So as I said, you need to find some other bug. So for example, you need to find a bug in the operating system, or in the compiler, or anywhere, and leak, for example, the value of the canary, or leak where the libc is loaded and stuff like that. As I said, difficult, but not impossible. All of this has happened before in the history, so attackers are very creative when it comes to breaking things. And yes, so that is all for return-oriented programming. Do you guys have any question? Did you understand it? Nice, cool, thank you. Oh, I find it, for me, it's like acknowledgement that at least I can explain it, because when I speak about it, it sounds so complex. Okay, perfect. So let's have a break, and in 10 minutes we can move on, and we will move to the last part, which is fuzzing. All right, so let's continue with our last part, that is fuzzing. So it seems it's a bit different from the binary exploitation that we did until now, but it can help you discover vulnerabilities that can be exploited, for example, in stack buffer overflows, heap buffer overflows, and stuff like that. Basically, what fuzzing is that fuzzing is a testing method of generating seamlessly random input for binaries and then like observing how the binaries behave, all right? Yeah, we have a definition then there. It's an automated software techniques to generate various test cases and observe. Yeah, basically that. You have different types of fuzzing. So again, as with binary exploitations, it depends on the amount of information you have. So for example, you might not have anything, right? Maybe you don't have a source code, you don't have the binary, you can just interact with it. So it's like a black box fuzzing. You can just observe how it behaves, and maybe you can alter the input based on the output. Like, it's a testing framework or technique, let's say. So what your goal is to test as most functionality in the software you are testing as possible, right? So that's why if you receive different output, then it's actually good for you. So you are trying to generate the input that will basically go through as many code in the target software as possible. You can do that more easily with instrumented testing. So that's the more common one. So you have a source code, and you basically adjust the source code somehow to track like what branches and what code you are testing and what you are not testing. So then when you generate some randomish user input, you can actually check if it triggered like a code that was not triggered before, right? And that's what you want. You want to go to as many possible branches as possible. I'm gonna show you some instrumented fuzzing in a while. So first, let's just talk about like what is this good for, right? So the good part is that you can do this in scale. Like you don't really. There doesn't need to be anyone like behind the computer, right? You can keep it running 24/7. You can keep running and like fuzzing some binaries, and probably you will find vulnerabilities that would not be found by like a human being if you were testing it, because you are putting like a random bytes into the target software, and it could be any length, and yeah, so. This is good, that probably you will find like vulnerabilities that you would not find otherwise, and it's quite easy to set up. Of course, it has like disadvantages. So if you are doing this, like you might trigger unexpected behavior. So for example, you trigger some syscall, right? Or you suddenly remove the whole file system or whatever, or the binary generate a file, and at that point you crash it somehow. So the binary or the target software cannot clean stuff after itself, and then it eats all your disk space, and your system will crash, and stuff like this. Let me show you some simple techniques of how you can fuzz very like in a kind of naive way. So one way is that you can take random bytes from the dev urandom device in any Unix machine. So for example, if you do this, let me go here back to our exploit lab. See, it's just outputting like a random bytes, whatever. So if I go to the first binary exploitation demo we had, it was this source code where we tried to override the local variable. And if I actually put this fuzzing output to the binary, see, it works, right? So if you use just this naive technique to fuzz this binary that you produced, you will find like a different behavior. You will eventually find a segmentation fault, and you will find that, okay, there is something wrong with this. Do you have an idea why this works? Like, how come sometimes it works, sometimes it's not? Well, the reason is that, as I said, the gets C function is reading until it finds like a new line, right? And this output from the urandom device is completely random. So sometimes there is a new line like in the beginning, sometimes like too far away. So it depends where the new line is, right? Because if it's too far away, then you will override the whole buffer, and then you will override also the return address with like junk, and the binary will crash. Yeah. Okay, so this is like one naive approach. In theory, as I stated here, this approach is sufficient to find all bugs. There is an infinite monkey theorem, which if you open, it says that if you imagine a monkey and a typing machine, no time machine. Monkey doesn't have a time machine, it has like a typing machine. And if you make it type randomly for infinite amount of time, eventually it will write everything possible, right? Including all works of Shakespeare and including anything. So this is like a similar approach. Like if you use this kind of fuzzing technique with like the view random device, assuming the entropy is truly random, eventually you would find every bug that is possible ever. Of course, it might take forever, but that's another thing. I forgot. Thank you. This is a time for secret code for online students, which I don't have it prepared here. In the drive? Okay, sorry guys, let me find it for you. I showed everything. There is nothing secret. Okay, so let's continue before I get the image. Next technique that we can use is a tool called Radamza. This one is also very interesting, like to play with. Now you can try to use it in your own containers, because I think in the exploitation lab there is no Git tool. But if I go to temporary. Okay, so let's just clone it, go there and compile it. Okay, so it's still compiling. This tool is very interesting because what it does is that you provide it input, like any input, and it tries to produce output that is similar to your input by whatever you provided, but it's different. So you give it a direction of what input of what output it should provide just for your use case. So for example, let's put 2024. Let's put this command. And see, it's producing somehow similar output that you can use in your testing framework. Or you can do like a calculation. See, then it's doing like different types of input to crash your application. I think this is pretty nice. Okay, so another tool is American Fuzzy Loop. A shortcut is AFL. Did you send it to me? Yeah. Okay, so sorry, online guys. Now there is a time for. Yeah, there is anything secret. Number 8. Voila, so it's bot bash. There are some deceptions in the background I see, so I guess if you use some tool to convert this to text, I guess to decept it. Okay, bot bash. I think it's enough. Perfect. So let's continue with our examples. So I was talking about American Fuzzy Loop, which is basically like a standard right now in the fuzzing techniques. It was developed by originally Google. Right now it's continued developing as AFL++ tool. And what it does is that it provides like a new compiler. So you give it your tool, and it compiles it with its own compiler. For example, if your tool is written in a supported language, and it injects in there like a code that is tracking the execution. And then they are fuzzing the binary, and they can track where actually the binary is, and they can update the input that is coming to your binary to actually test as most branches of your software as possible. This is very nice, and it's being used, if I'm not mistaken, in the Google Fuzzing open source projects initiative. So this is quite cool. So what Google is doing is that they have a project where they are fuzzing open source tools just to increase security, just to increase their security, and they are doing this 24/7. So if you have some open source tool and you would like it to be fuzzed by Google, you can just apply, and they will incorporate it and integrate it into their pipeline, and they cover all the costs, so you don't pay anything, and they are fuzzing everything that you code, and they are fuzzing every branch, whatever you do. If you push something to your repository, it would be fuzzed, and they will notify you if there is an issue. No. So I think there is like a threshold that the project needs to match in order to be like accepted. Like it needs to be, I don't know right now what are the requirements, but I think it needs to be like at least used by something. I think there's like a number of users or something like this. And if it's like, if it qualifies that it's used enough, and because their goal is to like increase security of open source projects and environment, so they will be fuzzing like projects that are actively used and developed and used by the community. Because they realize that these projects are usually developed by like small number of teams. Usually it could be just one maintainer or two. So then there are no like resources to do like big testing, right? And this is simple because it can be running 24/7. No one needs to be there. You don't need to know like too much about the project itself. You are just basically fuzzing it. And yeah, as it says, they state that they process tens of trillions of test cases every day because they have a lot of machines where they are fuzzing this. As I said, they are fuzzing every branch and in like thousands of projects, I think. And as of August 23, as you can see here, they found about more than 10,000 vulnerabilities and 36,000 bugs. So that is quite cool. Then I mentioned just two more fuzzers. If you are interested, you can look at them after the class. And before we end, there is one more announcement to be made by Muris.
Yes, hello. Just a brief announcement for the next class. We're gonna be doing some reversing. It should be fun and difficult, so yay. No, not scary, but no, it should be a nice class. So, but yeah, make sure that you still have the Wiresharks on your computers. We used them a few lectures ago, so we're gonna need it again next week. And also, this is for both people physically present and the online people. Make sure you have IDA installed. I've put a link there where you can download it and install it to your computers, because that's what we're going to use to reverse some binaries. So this is just like to give you a week in advance to kind of prepare, so that we can, if there are some issues, that we can troubleshoot before the next lecture, because we're going to have a lot of stuff to do so that we don't lose time on installing stuff. But we're going to remind you again on the matrix, so no worries. And yeah, also should I say about the assignment?
Oh yeah, you can.
Yeah, I mean, again, this week you can rest. We know it's midterms and test season, so like, good luck with that. And starting from next week, we're gonna have assignments back again. You can compete for the prizes and stuff, but for now, just get some nice points and on your other classes, and yeah, maybe get some rest if you can.
Okay, so that seems to be end of this of today's class. So please again just fill out the feedback. it's even for me, like, to know if I should maybe add like more examples for next year, or change something in the binary exploitation class, or generally anything you would like us to know. And yeah, that is it. We managed to end a bit sooner today than usual, but it was quite complex class. I don't know if you have any questions maybe before we leave about today's class or assignments or anything.
I just want to add that one of the feedback from last year was that the students wanted to see a little bit more of GDB. So this is feedback that students before gave, and now this year we introduce it. So it actually helps us a lot if you feel the feedback and you give us ideas, and if you find mistakes in the documents. Today there were 2 reported at least, so we already fixed them. So thank you for that. Yeah.
Okay, perfect. So if you don't have any questions, thank you for attending, and see you next week. Bye. In another room, 301, we will text you.